When you're multiplying numbers with scientific notation, you want to multiply like terms. So the 6 times the 4.8, and then 10 to the 4th times 10 squared. So I can rearrange them. 6 times 4.8, and then I'm just going to put that in parentheses. Make a little equal sign here so I know what I'm doing. And 10 to the 4th times 10 squared. So 6 times 4.8 is 28.8. 10 to the 4th times 10 squared. I add my two exponents, the 4 and the 2, and I get 10 to the 6th power. But I'm not quite done because I can't leave 28 because that is bigger than 10. So I move this decimal over here. So I have 2.88 times 10 to the 7th power. I basically took away a power of 10 here, so I needed to add a power of 10 there. In this equation, I'm going to treat it the same way I did number 11. I'm going to divide like terms. So I start with 1.5 divided by 5, and that gets me 0.3. So that gets me 0.3, and then 10 to the 7th is going to be, well, 10 to the 7 minus negative 2. So it's going to come out to be 0.3 times 10 to the two negatives cancel out, times 10 to the 9th. Not quite done. I got to move that decimal point over. So I get 3 times 10. And what I did is I added a power of 10 here, so I must subtract a power of 10 from my 10 digit. I get 10 to the 8th. And the answer to the one before, forgot to box, was there. This question asks, how many red blood cells does your body produce in one day? Well, we start with 2 times 10 to the 6th blood cells per second, and we need to convert that to day. So first I'm going to change, get 60 seconds over 1 minute, and then I have to get rid of minutes, so I have 60 minutes into 1 hour, and then I need to get rid of hours, and there are 24 hours in one day, and you'll see that my seconds will cancel out, then my minutes will cancel out, my hours will cancel out, and then my final answer will be some number per day. So I just need to multiply those out. I'm not going to have enough room over there, so I'm going to write it down below. When I multiply the numerator, I have 172,800 times 10 to the 6th power blood cells per day. I need to convert the numerator to scientific notation. So I'm going to move the decimal 1, 2, 3, 4, 5. So I'm going to add, 1.728 times 10. I move the decimal 1, 2, 3, 4, 5 times, so I add that to 6. So that is my final answer. 1.728 times 10 to the 11th red blood cells per day. In part B, it says you're going to give 1 pint of blood, and that accounts for 2.4 times 10 to the 12th red blood cells. How many seconds will it take you to replace that? So what you're going to do is just divide that by how many blood cells you create per second, and we end up with, let's see what we end up with. 1.2 times 10, 1.2 because I divided 2.4 by 2, and 10 to the 6th power because I'm going to subtract my exponents, 12 minus 6, and I end up with that. So that's the first part of the question. The second part then how many days is it going to take? And we go through the same thing we did right there. We have 2.4 times 10 to the 12th, and we're going to divide by how many blood cells you produce in a day, which we found in part A, which was 1.728 times 10 to the 11th. So we take 2.4, we divide by 1.728, get 1.39 times, and then we're going to subtract the exponents, 12 minus 11, so times 10 to the first power. We don't need to write the 1 in. So, there you go. So it takes you about almost 14 days. Number 14 asks you to substitute in values for variables. So in this case, y equals 3 times 5. X is negative 1. So we substitute in negative 1 for x. And we get 3/5 because that negative exponent makes 5 go to the denominator. Then it says let x equal 2. So we go ahead and we say y equals 3 times 5 squared, which is 3 times 25, which is 75. So the second part is 75. And the last bit of it says let x equal 3. So y equals 3 times 5 cubed, which is 3 times 125. So we get 375. The next problem is f of x equals 1/2 times 4 to the x. And remember, f of x is the same thing as y. It is no different. It's just saying the function in terms of x equals 1/2 times 4 to the x. Same thing as y equals 1/2 times 4 to the x. So let's let x equal negative 1 to start. So we have f of x equals, and actually what you would want to do is instead of saying f of x, you can rewrite that as f of negative 1, and that just means you're substituting in negative 1 for x, equals 1/2 times 4 to the negative 1, which is 1/2 times 1 over 4, because that negative exponent puts the 4 in the denominator, and we end up with 1/8. Then it says let x equal 2. So again, we substitute f of 2 equals 1/2 times 4 squared, which equals 1/2 times 16. We can take 1/2 from 16 and get 8. Lastly, it says let x equal 3. So f of 3 equals 1/2 times 4 to the third power, which equals 1/2 times 4 to the third is 64, and your final answer then is 32. The next problem, f of x equals 4 times 0.95 to the x power. Let x equal negative 1. So f of negative 1 equals 4 times 0.95 to the negative 1, which is 4 divided by 0.95, which comes out to 4.21. Then we're going to let x, we'll do that in black. We'll let x equal 2. So f of 2 equals 4 times 0.95 squared, and 0.95 squared is, so 4 times 0.9025, 3.61. And the last one, x is 3, so f of 3 will equal 4 times 0.95 cubed. We cube just 0.95, and we get, and we'll come down here, 4 times 0.857. And in your calculator, there's some more decimals, and you would just leave them and multiply that answer by 4 so you don't round off until you get your final answer. In this case, it becomes 3.43. This problem asks you to graph 1/2 times 2 to the x. So what I'm going to do is set up a table, get some values. If I plug -2 into the equation, so that's 1/2 times 2 to the -2. I then have 1/2 times 1/2 squared, or 1/8. And put that there. -1. So 1/2 times 2 to the -1. 1/2 times that negative exponent makes another half. So I get 1/4. 0. 1/2 times 2 to the 0 power equals 1/2, because anything to the 0 power equals 1. 1. So now 1/2 times 2 to the first equals 1. And plug in 2. 1/2 times 2 squared equals 2. You know what? I'm going to try 3 as well, just to see what happens. See what's going on with this. Times 2 cubed, and that's going to be 4. I'm going to go ahead over here, and now we'll try to draw a straighter line than that. Plot some of these points. Okay, so plot them in red. So -2, 1/8 is very small. I'm just going to guess it's here. -1, 1/4 is a little bit higher than that. 0, 1/2, well, it's going to be about there. 1, 1, 2, 2, and 3, 4. So up to here. So I think you'll see, we'll see if we can draw this, it's going to be going like so. And this would be an example of exponential growth. And it's exponential growth, you'll note, because what you're raising to a power, that 2, is greater than 1. I'm going to go through the same exercise here. I'm going to plug in -2 to begin with. So 2 times 1/2 to the -2 power is going to equal 2 times 2 squared, or 8. Plug in -1. So 2 times 1/2 to the -1 is going to equal 2 times 2. You'll notice that the 1/2 becomes a 2 when it's raised to a negative exponent. So that's going to get me 4. 2 times 1/2 to the 0, 2. So 0, 2. 2 times 1/2 equals 1. Plug in 2. 2 times 1/2 squared is going to equal 2 over 4, or 1/2. And again, I'll just try 3 as well. 1/2 cubed is going to equal 2 over 8, or 1/4. Now let's go ahead and graph this set of points. Alright, again, graph it in red. So -2, 8, it's going to be, I've run out of room, but it's going to be up here. way up here somewhere. -1, 4, take it down to here. 0, 2, right there. 1, 1. 2 is at 1/2, and then it gets smaller and smaller. So this graph is going to go this general direction, and an example of exponential decay, and it's exponential decay because of that 1/2 right there. That number is less than 1, which makes it decay. Number 19 asks, if you have $2,000 to deposit or invest at 5.2% at an annual rate compounded quarterly, how much do you have at the end of 2 years or 5 years? The formula we're going to use is this one here, R over N times T, where P is your initial amount, N is the number of times that you're compounding it per year, R is your interest rate, and T is the number of years. So let's go ahead and plug in those values. So we have $2,000, 1 plus the interest rate is 5%, so 0.052 quarterly, so 4 times a year, raised to the 4 times 2. And we end up with $2,000 times 1.013 raised to the 8th power. So 2,000 times 1.013 raised to the 8th, and you end up with $2,217.71. So for 5 years, same problem, but the only thing that changes here is the period of time. So this will be 4 times 5. Alright, so again, $2,000 times 1.013. This time it's going to be raised to the 20th. So we get $2,589.52. So there's 5 years. Here is 2 years. In this problem, you have a car worth $30,000, but it loses value. So, what is the decay factor? Well, the decay factor in this case is 0.85. And what does it mean? Well, it's how much value the car has after each year. So basically, it's losing 15% of its value each year, which means it has 85% left. So estimate the car value after 1 year. So 30,000 times 0.85 to the first power. And you get $25,500. That's how much it's worth after the first year. After the 4th year, so 30,000 times 0.85 to the 4th power. So 30,000 times 0.85 raised to the 4th power. $15,660.19. So that's it. Good luck with this.